In this lecture, I continue with the analysis of the spectrogram that has been measured. Okay. So, what happens is exactly like in the intensity autocorrelation technique, the temporal gating is done by splitting the pulse into two copies with a relative delay tau. Gating, as I had explained before, it is just the second pulse which is called the gate pulse. Two pulses overlap spatially and temporally in the second harmonic generation crystal, which happened even in case of the intensity autocorrelation. The second harmonic generation crystal produces a second harmonic signal. Okay. The strength and the shape of the signal depends on the temporal and spectral properties of the original pulse. Okay. Using an iterative algorithm, the temporal amplitude AT and the phase phi t of the pulse is retrieved. You remember AT was the amplitude, which was the guess part, and phi t was the phase. Okay. So, by an iterative algorithm, the temporal amplitude and the phase is found out. And once you have the temporal amplitude and the phase, you have the total pulse. Okay. So, now what is that algorithm? Okay. The algorithm basically the algorithm follows these equations. Okay. It is following these equations, but let me give you exactly how the algorithm comes into the picture. This is the frog algorithm. Okay. So, I have this initial ET is guessed on, say, let it be a Gaussian. That means I am guessing a pulse first. This is not, I am trying to find out what is ET, the shape of ET, how the ET function varies with time, that is my aim, but I do not know that. I have taken a spectrogram, I have taken an experimental spectrogram there, okay. And now I have to retrieve this ET, okay, from this algorithm. So, my first guess is a Gaussian. It is always nice to take a Gaussian curve. Now, use this guessed Gaussian to generate the nonlinear signal E signal t tau. Okay. So, this has come, it is E t into E t minus tau, as you remember we had put. So, that is E signal t tau. With this delay time, we have got what is this nonlinear signal. Nonlinear signal means the second harmonic generation signal. Okay. So, I have got that signal. Okay. Now, what is my next step? Next step is compute frog trace by Fourier transform S omega tau. Okay. I have to compute it. Remember, I have measured it. So, I have written it as S calculated omega tau. But what I have measured is S omega tau. It is not the calculated, this is the measured pulse, experimentally measured pulse. Here I use the symbol S calculated. Okay. So, I have this, I have the E signal. If I take the Fourier transform of this, I am going to get S omega tau. That means the calculated spectrogram. Now, you have two spectrograms, one is the calculated one here and you have the measured one. You find the error between these two from the frog trace and the measured spectrogram. The error is given by sum of all those points, you take each of those points, that is why it is a sum of over all the frequencies and all the delay times and the intensities that you have got there. So, the error is equal to S calculated omega t minus S measured. Here in this case S measured I have put in place of S omega t, okay, just to distinguish between calculated and measured. So, I find the error, I take this subtraction and I see is the error very large or both of them are similar. Okay. When I start with my first guess, I am sure they will not be similar. Okay. There will be a difference. So, I have an error and I keep it aside, keep that error aside. Now, replace the amplitude or the calculated frog trace with the measured amplitude of frog, keeping the phase unchanged. Okay. Now, I have a new frog trace or new spectrogram, which I have called it with a dash S dash omega t, and that is square root of the measured. Okay. This part is measured, root of this because it is the intensity and here I am taking the field. Okay. So, S measured, I take the root of this is known, and I have a calculated phi. I have a calculated phi because I have taken a guess of what kind of pulse it is, and once I have taken a guess of the pulse, I have made a guess in that in the phase factor also. Okay. So, I do nothing, this is the calculated part, but I have multiplied it with that amplitude of that measured part. Okay. And then what I do is I take the inverse Fourier transform of this. So, if I take the inverse Fourier transform of this, I will get in terms of time t and tau. Okay. So, that becomes E signal t tau. E signal means exactly like this E signal, but we have done some manipulation here. So, I place it as E dash signal t tau, which is the inverse Fourier transform of this. Okay. Then I define the guessed field. I redefine the guess, okay, using E dash signal t tau. You know, this part has come about because there is a partial measured part and a partial guessed field. Okay, the part that has been guessed. It is a combination of both. So, this inverse Fourier transform gives this new signal, okay, E dash E t. I had started off with E signal t tau. Now, I have a new signal E dash t tau. I go back again into the loop of the algorithm here, and I do again this, again I do a calculation of the frog trace Fourier transform. Means if I take the Fourier transform here, I will get S calculated again. This is a new set of data. Okay. Again I go through this loop, I find the error between the calculated and the measured. Measured has remained the same, whatever was the earlier measured. Has the error become less or more? That is up to me to define. I define an error. Okay. I want it to be 0.1 or I want it to be 0.2. Depending on this error, you will have a larger error in your the measured pulse or not such a big error. So, this is again you keep in mind. Now, in your second iteration, has your error increased or reduced? If it has reduced, definitely you are going in the right direction. So, again I go ahead. I assume that my error has reduced. These two minus this has reduced. So, again I repeat the same thing, replace the amplitude of the calculated frog trace with the measured amplitude of the frog trace, keeping the phase unchanged. So, I go through this process once again and take the inverse Fourier transform, again I do that, and I come to a new E dash signal t tau, and I keep on putting in this loop and it goes on in that loop until my error is a small value or to my satisfaction. Okay. A frog error has proved to be an effective measure of convergence. Okay. So, the whole idea of this error is to see when this loop or your ET converges to some final value. That is exactly what you want. You want that unique solution ET. So, you 4 or 5 times you keep on going through this loop until your error is very low. Once your error is very low, you know it has converged to a certain value of ET, and that is the measure of your pulse. Okay. And once you have ET, which is the field, you can take the mod square, you will get the intensity, and you will get the intensity of the pulse that you desire. So basically the spectrogram has done the job. The pulse, which consists of frequencies at different times, the intensities of those frequencies at different times, that is what you have measured. Okay. So you have been able to deconvolute the pulse or extract that pulse from this spectrogram. So the spectrogram is a very important measurement. Okay. So finally, from the intensity autocorrelation technique, I have derived the frog autocorrelation technique. I don't know if it is called autocorrelation. Frog has its own name, frequency resolved optical gating. Okay. Frog because F is for frequency, R is resolved. It is an acronym for this whole thing, and the optical gating that we have done, and we have resolved all the frequencies, and that is how we get what we get. Okay. So this is the way of measuring the pulse. Now there are a few ultra short pulse measuring systems which I won't describe here, but the basic concept is on the concept of this autocorrelation and the frog, with the finer details that have been finer details of the experimental side that has been taken care of. So one of them is Grenoille, it's called Grenoille, grating eliminated no nonsense observation of ultra fast incident laser light E field. Okay. So it's a long name and the acronym is Grenoille. So this was sort of devised by some French researchers who were having a lot of fun in the lab, I'm sure, because Grenoille is the translation of frog in French. So here they have got this. So this is actually, this measures a single shot pulse. So you don't need multiple shots to get the data. One single shot of the pulse, and so this is a little more accurate than your frog pulse, because each in the frog also, if you have a multiple pulse, means one pulse may not be the exact replica of the other. They may be slightly different. So you take only one shot and you take the measure. So you have a more accurate measurement with the Grenoille. Then there are some other methods called the tadpole, temporal analysis by dispersing a pair of light E fields, tadpole. See, these people were also having a lot of fun. They all wanted to stick to something to do with a frog. But here there is also spider, spectral phase interferometry for direct electric field reconstruction. Okay, so that's called spider. So all these researchers had a lot of fun doing all this, given lots of fun names. But okay, the basic concept and the principle remains the same as a frog and the autocorrelation technique. So here I stop talking about the pulse measurement system. Those who are interested can go through all these refinements in the pulse. In fact, if you are working on that, on some laser, ultra short pulse laser, you definitely should know these details, because measuring the ultra short pulse is a very important part of doing any experiments with these ultra short pulses. Okay. So now I just shift gear a little bit and I go to some of the some of the uses of lasers. I have already spoken about the exotic use, which is the fusion process. Today I will go through some little more mundane uses of lasers. Mundane may be, but definitely very, very important and very, very popular, okay, uses of lasers. So, some of the laser applications are as follows. So, if you see, what I want to say is the first thing that comes to your mind when you want to use a laser for certain application is that lasers have a high power. They can give high intensity. Okay. So, my first application will be on how do you, on the property of the laser that is used for material processing, which uses the power and the intensity characteristic of the laser. Okay. So, they are used for laser welding, laser hole drilling and laser cutting. Okay. All three of them use this power and intensity capability of any laser. But just the laser itself will not do the job that you desire. So, you need some other optical elements which come into the picture, like you want a small focus in order to get a larger intensity, or you want a tinier beam. So, you will put something like a lens, okay, lens or some optical system which focuses the beam. So, you need all these optical elements too, which are attached to the laser and to get your final application done. Okay. Now, I want to just speak about what are the properties of the lasers that is required in this case. So, it is all that property is, of course, the power and the intensity is the main thing. So, if I have a lens here, I am this is my laser light which is coming and it gets focused to a small point. This is the small point. Okay. And in red I have just shown the wavefront. There is a plane wavefront before the lens, and after the lens it becomes a curved wavefront or phase front, and because of this curvature you get this focusing. But along with this focusing part, you have to take care of the diffraction effects too. Okay. So, one has to use the focusing element like a lens to increase the intensity of the beam, and the laser beam has a well defined wavefront which may be plane or spherical, and the diffraction effects also come into play. So, what do I mean by the diffraction effects? When you focus that beam to a tiny spot, it is not really as tiny as that. If you look at a bigger picture, you will find these rings. You know, it is focused to this spot, and this spot is so bright that you may not even be able to see how tiny this spot is. Okay. So, all that brightness is because of all these diffraction which is happening. So, it is not a clean little spot like this in the center. It has these annular rings around it. These are called airy patterns. So, if you were to take a cross section along this line, the intensity along this line, this is the intensity. At the center the intensity is maximum, and then you get all these sort of patterns. These are called airy patterns. This happens even if you take a TEM00 mode. TEM00 mode means it has the perfect cross-sectional beam. If you remember the modes, TEM, there is TEM11 mode, there is TEM01 mode, TEM22 mode, 20 mode, and all such. And none of them, only this TEM00 mode has a perfect circular structure. And the intensity profile is a Gaussian profile, with the center having the maximum and it falls out at the two wings. Okay. While the other modes, remember, they looked something like this, or they looked something like this, all these other modes. And these kind of modes are very, very difficult to focus, or even if you focus them, most of the energy would have gone off in this outer rings. Only the TEM00 mode gives you a decent kind of a cross section. And suppose you are particular about exactly it being a very clean kind of focal spot, then by putting apertures and such, there are means of throwing out, eliminating these annular rings too. Okay. But then if you throw out those annular rings, you are throwing out a lot of energy also. Here, if I show this, if lambda is the wavelength, A is the radius of the beam, that means here radius of this beam, F is the focal length of the lens, focal length of this length, and B is the focal region, means this. I call it a region because it does not focus to a spot, it is a big region like this. Okay. Then B, that means this focal region, B is equal to lambda F by A. This can be derived very easily. You can look up some optics books and you will come to that derivation. So, it can be derived very easily. So, you will get this B equal to lambda F by A. Okay. So, you see there is lambda, the wavelength that you are using, that is also important when you focus it, and that is important for these diffraction effects. And if P is the power of the laser beam and I is the intensity, then intensity is powered by area, that you know. So, P upon pi B square, P A square upon, just substituting this, P A square upon pi lambda square F focal length square. So, you see here you can get a very tiny spot if this can be tiny, if your lambda is small. Okay. So, you want you have to choose your lambda also when you are using it for the kind of applications that you are using. Okay. And then about 84% of the light energy is in the center, in the first dark circle, that means here 85% of this energy is here. And if you eliminate all this, you have eliminated 7% of the energy which is found in these two annular rings. So, if you put an aperture, you have lost out 7% of the energy. So, you have to keep this in mind when you are designing a optical system which will focus in order to carry out laser welding, in order to carry out hole drilling, in order to carry out the cutting of any material. Okay. So, you have to pick up the right laser wavelength. Okay. You have to pick up the right power for that particular job. You have to choose the right optical systems in order to get the beam focused or the focal spot size that you desire. Okay. So, here I just give you some examples. In this example, I have just taken a 1 watt laser beam, okay, and A is 1 centimeter and the focal length is F equal to 2. So, intensity I at the focal spot works out to be, if you just put in all the formula in the previous, all these numbers in the previous formula, you will get 7 into 10 to the power 6 watts per centimeter square. So, this is the intensity that you can focus to when you have a 1 watt laser beam. Just as an example to give you an idea of the magnitude of the intensity that you might get from a 1 watt laser. Okay. So, some of the lasers that are used are ND YAG laser, which is 1060 nanometer, and you will get easily 5 kilowatts of power. So this is a CW laser. Carbon dioxide lasers are much more efficient, and it is in the 10.6 micrometer. You will get around 50 kilowatts of power. And then there are the excimer lasers. Okay. That is this comes in the ultraviolet. You will get around 500 watts. So the ultraviolet lasers are very attractive for finer cuts or finer details of any pattern that can be done, because you see the wavelength is very short. It's in the ultraviolet. So the focal spots will be also very small. Okay. So this is ideal for very accurate cutting or hole drilling. Okay. Then your laser could be a continuous wave laser or a pulse laser. Many of the carbon dioxide lasers that are used for this material processing, cutting, wood cutting or metal cutting, are continuous wave lasers. But there are some which are pulsed too. Quite a few of them are pulsed. Then in pulsed ruby laser is also used for welding. Energy of 5 joules with pulse duration of 3 nanoseconds, welding of 0.18 mm, thick stainless steel plate, and it has a repetition of 20 pulses per minute, and it is focused to a spot of 1 mm, and the intensity is around 10 to the power 3 watts per centimeter square. Just to give an example of this. Okay. Now this picture just have a, so depending on your application, as I have said, you have to choose the power, you have to choose the pulse length. In case of welding, when two materials are welded together, you don't want to lose material. So you don't want a very short pulse, because short pulses always evaporate that material, and you don't want the material to be lost, but with a short pulse the material is lost. So having a longer pulse may be an advantage. So these are the parameters of the lasers which you have to take care of. Here you see in this, this is the depiction of, this is a lens and this is a laser. This is a long pulsed laser beam. Okay, this is a long pulsed laser beam which is focused, and it's drilling a hole. Okay. Now what happens is, if it is a long pulsed laser beam and also the kind of wavelength that you have chosen, it will cut, but it will never be a clean cut. There will be burr here, B-U-R-R, burr. So you'll have edges and all. Once the cutting is done, you have to repolish these edges, and it's not a perfectly cut thing, and there will be shock waves which are going here and there and everywhere. So and that will cause certain disturbances in your material. So this is what a long pulse does. But if you have a short pulse, very short pulse, before the material knows, the short pulse has come and gone, and it has evaporated all these side materials completely. So your cut becomes a cleaner cut. So short pulse, in order to get cleaner cut, you will need a short pulse. If it is not that, if you are not particular, the power is important, it's a thicker steel material where this side things don't matter much, then you can go in for a long pulse or a CW laser also. But the ultimate case of precision cut, ultimate case of that is seen in this example. Okay, it's a lovely picture. This is a coronary stent in medicine. You see the stent, you can imagine the one that is going into your arteries and veins, how fine it has to be. So you have to cut it in such a fine way. Okay, this stent, which which will be closed initially and then expanded in your artery. So, the fineness of this is exhibited in this picture. So, again you have to choose the laser wavelength very well, you have to choose your focusing optics well, and whether it will be a pulsed laser, what is the duration of the pulse will determine how fine and clean this kind of a cut is. Okay. And another very popular application is LASIK, where your myopia is corrected. That means the cornea of your eye is cut, which changes the focal length of the lens of your eye, and you have all the usual light focusing exactly on your retina. Basically, the power of your lens becomes better. Okay. So, can you imagine, it is a biological system. This also uses very short pulse laser. Excimer lasers were used at one time. Now, I think you can have frequency double or frequency triple ND YAG laser, which will give you in the ultraviolet ray, and they are short pulses. So, it gives you a nice clean cut in this, and I believe this is done in few minutes in a hospital or a clinic, and it has become very popular. Okay. So, I stop here, but in my next lecture I will talk about another very important use of lasers called the LiDAR. And of course, I will speak about the Nobel Prize, Nobel Prize that was won in 2018 for using the pressure of a laser to move tiny particles. Okay. Very useful in biological systems. Okay. So, I will be describing these two.